Welcome back everyone, and in this video we're going to discuss autoencoders. So for the first time we are leaving the area of supervised learning where our main aim was to predict a target variable, and now we are going to autoencoders, which for instance can be used in the area of so-called unsupervised learning. But it kind of is something in between if you are really taking it, I don't know, if you really try to define it specifically. I find it hard because basically the idea of autoencoders is to have a certain input, so usually consisting of certain feature variables, and then bringing this to a lower dimension, which simply means to use less variables in comparison to the dimensionality of the input features, but in the end generate out predictions which are as close as possible as the input features. Sounds very, I would say, confusing in the beginning, but hopefully makes more sense in a few more minutes. I really like autoencoders a lot, to be honest. I think it's a very interesting concept and it can be used for many things. But I would say its most obvious purpose is dimensionality reduction. So let's first in this video go through the, hopefully in a few more minutes, through the, I don't know, theory is said too much, but a little bit to the formal definition of an autoencoder, and then I will show you two examples. One is a synthetic example which I made up in my mind, and the other is an example for which we could really use autoencoders in the area of finance. We will use an autoencoder to generate an algorithm which could be used by you to build your own ETF, so your own exchange traded fund. So the principal idea is not to take a look at any target variables anymore, and we will have a certain amount of feature variables as before. So for the moment, as in our example, it will be the log returns of single companies. Okay, so and now assume, I don't know, we have 10 companies or 100 companies. So, and further assume we are more interested not in the development of a single company, but more like in what's happening here systematically, meaning, loosely speaking, how is the development on average for these companies. So if we would use an average, then we would reduce the dimension of, say, 10 companies. If we take the daily average of the log returns of each stock company to a single value, to the arithmetic mean, by using the arithmetic mean, we would condense the information of the 10 values into one value. And with autoencoders, we are doing more or less the same, but we can choose. We can choose if we want to transpose the information of 10 companies into a single number, or for instance into 3 numbers or 5 numbers, because obviously sometimes a single number will not be enough in order to really have a condensed form of the information that is provided by the 10 companies. But I would say from intuition, what we want to do when we reduce the dimensionality is that we condense information, meaning we use less variables than in the beginning, but we try to retain the information that is kept in all those variables as best as we can. But as we're reducing the dimension, usually we will lose a little bit of information. Okay, so that is our purpose of dimensionality reduction, and dimensionality reduction can really be important, especially, for instance, if we want to use it later for a model which then will be used for supervised learning. So in many cases, we may have a lot of feature variables, like 100 or 200 or 300 or even many more, and then we will run into the curse of dimensionality, okay? And that can be problematic, and we can reduce this problem by using a lower dimensional representation of the original feature variables. How are we going to do this with neural networks? Okay, so this is another example. So given a feature with n dimensionalities, this is always the number of features that we have. What we're trying to do is to generate a lower dimension, so NL, which is smaller than n, in order to have a lower dimension but retain the information that is provided in the original features. And the purpose of this can be seen here again in another example. So even though this sequence is way more shorter than this one, you will directly see here that there's a certain pattern is here given here, and it is enough to memorize a single number in order to have the information of all those values here. Okay, and that is basically what we're trying to find with autoencoders, that we have some regularities among different variables, but we may observe certain patterns which makes it enough, or which suffices if we have a lower amount of numbers but still have as much as information as possible as we had in the original data sample. Okay, then what are we going to do? We are combining two layers to succeed here. First of all, we'll need a function that gets the original information provided by all the data features. This function is going to be parameterized, which we highlight again here with the theta, the big theta letter here. And then we want to take a look. So we have a model taking the original data, doing something which in the first step reduces the dimensionality of the original data, but then in the end will make a prediction out of the lower dimension in order to generate the original data. Okay, let me just go to this visualization here. It makes it much more easier to understand. Okay, so as we know it from our forward neural network, we have an input layer including the input features. So here we have n features. Then with the autoencoder, we first use typically a fully connected or a dense layer. Later, in more advanced autoencoders, we can also use here recurrent or convolutional layers. But for the moment, to understand it, this is going to be a fully connected layer, which brings the original feature variables into a lower dimension, meaning we use less neurons than we had in the beginning. Okay, here we have n feature variables, and then this should be NL here. We have NL hidden neurons, and NL is supposed to be a smaller number. So as you can see here, assume it would be 10 feature variables, and then we would bring this down to 3 values after the first layer, because we're using 3 neurons here. And what we and if we would have been now in a typical situation where we are going to use we're going to build a prediction model, then what we would do here is, for instance, if we would need a single prediction, we would further bring those 3 neurons down to a single value and use this value as a prediction. But for the autoencoder, what we're trying to do now is, out of these 3 neurons, we're making as much as output predictions as we had in the input feature dimensionality. Okay, so if we have 10 features in the beginning, then we first bring those features down to 3 dimensions in this example here, and with these 3 numbers we try to make a prediction for 10 numbers again. And basically your intuition tells you that very likely the recreation cannot be done perfectly again here, especially if we have more than one data sample. And so the autoencoder is basically a neural network with a prediction of the dimensionality that is equal to the input dimensionality. And then again, we will use the squared deviations of the original value and the predicted value here. So x1 minus hat x1, x2 minus hat x2, and as always, we are squaring those values. And this is the loss function that's going to be minimized. And by minimizing the deviation between the original value and its recreation, we forcing the input features here, so here the reduced dimension, to retain as much as information as possible as was given by the input information, okay, by the original features. But we hopefully succeed in doing this by using less values here than we had in the input layer. And this is what we are referring to as one possibility of dimensionality reduction. And even now, for the moment, it may not seem to be super important to you to have the ability to reduce dimensions, but this can, for instance, be very beneficial if we first, condense the information of many features into a lower dimension and then use this lower dimensional representation of the original data in order to build a supervised learning model. Because of the so-called curse of dimensionality, I would here highly recommend you to read in the book Hands-on Machine Learning the explanation about the curse of dimensionality. I think it's very well explained here. So formally, what we have here, like first of all, out of the input information, we will generate here, especially if we use a linear autoencoder, meaning we do not use any activation function here or any nonlinear activation function. We generate the reduced dimensionality of the original data by this mathematical operation, and then we bring it back with another weighting matrix, including parameters, to the original dimensionality. And this is our loss function, but as I described it before, okay? The first part here is called the encoder. We are encoding the original data to the reduced dimension, and then to bring the reduced dimension to the original dimension, we use the decoder, okay? And that is why we have an encoder and decoder, and this is called an autoencoder. Here, this special architecture I would refer to as the linear autoencoder, because as I said before, we're using no nonlinear activation functions. And to give you a better feeling what is meant by keeping as much as information as possible, this is just a fictional example, and here you can see original data in 3 dimensions, okay? And here you see 3 arbitrary points in those 3 dimensions. After I used a autoencoder to bring those 3 dimensions into 2 dimensions, I still, marking these purple dots here, and those are the same, or those would be the corresponding dots in 2 dimension to those of those given here in 3 dimensions. And as you can see here, regarding how far those purple dots are away to each other and then to the other points, this is almost or nearly identical. So the behavior and the relation between those points, and each point is representing a certain observation which would be given in a data sample, so a single sample. So here we have a sample with 3 original features, and for instance for this one, then probably this would be the corresponding representation just using 2 values. On those 2 values are the can be interpreted as the condensed information of the original information that was given by the 3 variables here. So, but basically this should hopefully give you an idea that retaining information, meaning that in the dimension given, the relationship between and among the variables are kept as similar as possible. Using, of course, is, as I said, simply the dimensionality reduction, but it also can be used for other things. For instance, generating new and unseen data. There's such things as variational autoencoders, and instead of like the forward neural network structure, we could also use an autoencoder using recurrent and convolutional layers. If the original data here has very unique and complex and nonlinear relationships, this type of architecture wouldn't be enough, very likely, in order to build a model which is really able to bring the reduced dimension back to the original dimension, and hereby retaining the relationships as they are in the data. That is why, of course, we can generate a little bit more and advanced and complex architectures of the autoencoder. That is, for instance, called a stacked autoencoder, meaning we're using more than one layer in between. And here also typically our aim would be the dimension here in the middle. So even though we are making a recreation of the data, still our main interest would lie in those values that will be given here. So you can picture it like this. Basically what we want to have is later, after we built the autoencoder and after we fitted the autoencoder, we use the original data and then bring it back to a lower dimension, and we use the lower dimension of this original data. But in order to make sure that the lower dimensional representation really keeps as much as information as possible from the original data, first when building an autoencoder, this is done. To make sure that the information is kept is to take a look if the model would be possible to make regenerations of the original data, which is as close as possible by simply using only those 3 values here. So basically what we have here are 2 models. The first model aims to just bring the dimensionality down here, and the second model tries to make a prediction out of the lower dimension into the higher dimension again. All right, I would say this is like the most important part when it comes to have at least a certain formal understanding what an autoencoder is. But I would say, when you see it, how it's done and what it does, it gets way more easy. And that's why in the next video we're going to switch to an example where I will show you the usage of an autoencoder with a fictional example, and then I would guess that it will be way more understandable and interpretable by yourself. Okay, so please go immediately right now and watch the next video, and see you there.